Thanks for watching my video today. Let's prove the integral representation of gamma function. Then is the integral from 0 to infinity, which is a improper integral. So x to the s minus 1 e to the negative x dx, which is gamma s. Okay, we know the real, and for this gamma, always real part of s is greater than 0. This also we are going to prove it. Okay, that what we call the convergent sequence, convergent series, or convergent integral. So the convergence of this gamma function is real part must be greater than 0. So s is a value. Okay, you can substitute 1, 2, 3 natural number. Okay, but it cannot be 0. If it is 0, it will be divergent already. So let's prove this. So our integral, let's say I, which is integral from 0 to infinity x to the s minus 1 e to the negative x dx, and this part we have already proved, right? This one in terms of limit. So since e to the negative x is limit n tends to infinity 1 minus x by n to the power n, this we have already done. So this, in place of e to the negative x, substitute this limit here, and you get this. I is equal to integral from 0 to infinity x to the s minus 1 in place of this limit n tends to infinity 1 minus x by n to the power n dx, right? So this, since this limit is constant, so coming out here, limit n tends to infinity, integral from 0 to, since this is limit is n tends to infinity, right? So this is also infinity, so if it come out, so it will be n, right? If n tends to infinity, meaning if n is infinity, right? This is infinity, or this is also infinity, this is also infinity. So if this one coming out here, so this is the upper limit is infinity, so it will be n, right? Because of this, because of the limit. So limit n tends to infinity 0 to n, and x to the s minus 1 minus x by n to the n dx. Now substitute x by n is equal to y, so x is ny, right? So dx is n dy. So you get I is equal to limit n tends to infinity. When x is tends to 0, y will be 0, right? And when x tends to n, so y will be 1. Okay, so x is nothing but ny, so ny to the s minus 1 minus x by n is y, right? 1 minus y to the n, and dx is n dy, right? So we just limit n tends to infinity, and this here is n minus n to the s minus 1, n to the s minus 1, right? And here also n is there, so by power series, by exponential law, it will be n to the s only, right? So n to the s is again constant, so it coming out here, and we are left with integral from 0 to 1 y to the s minus 1 minus y to the n dy. Now we are going to use integration by parts, so taking y to the s minus 1 as second function and 1 minus y to the n as first function, and using the integration by parts, we have I equal to limit n tends to infinity n to the s. Now take the integration by parts, so 1 minus y to the n, right? This is first function. Integration of this will be y to the s upon s, and or integral from 0 to 1. So minus integral from 0 to 1, differentiation of the first function, differentiation of 1 minus y to the n minus 1 is, no, differentiation of 1 minus y to the n is n, 1 minus y to the n minus 1, into integration of y to the s minus 1 is y to the s upon s dy, right? Therefore, if you put here 1, so 1 minus 1 0, so this will be 0. If you put 0, so y is 0, so this whole term will be cancelling out 0. So we are left with only this term. It will be limit n tends to infinity, negative is here, right? So negative n to the s into this n here, s is here, and we are left with integral from 0 to 1 minus y to the n minus 1 y to the s dy. Similarly, this is take for this first function, this second function, and use the IBP. So limit n tends to infinity minus n to the s into n upon s, which is take the, so 1 minus y to the n minus 1, integration of y to the s is y to the s plus 1 by s plus 1 from 0 to 1 minus integral from 0 to 1, differentiation of this will be n minus 1 minus y to the n minus 2, right? And integration of this y to the s plus 1 upon s plus 1. Now if you put here 1, then this will be 0, and if you put 0, this will be 0 again. It will cancel out again, so we are left with only this one. So this minus and this will become plus, right? And to the s into n minus 1 upon s, this, right? S plus 1 here. So we are left with integral from 0 to 1, 1 minus y to the n minus 2, right? Y to the s plus 1 dy. So let's do one more term. So taking this as first function, this as second function again. So limit n tends to infinity, n to the s, n minus 1 by s plus 1. Now integration by parts, take here 1 minus y to the n minus 2. Integration of this, y to the s plus 2 upon s plus 2 from 0 to 1. Minus the integral from 0 to 1. Differentiation of this is n minus 2, 1 minus y to the n minus 3. Integration of this, y to the s plus 2 upon s plus 2 dy. Right? So now next will be this. Now continue again here, I equal to limit n tends to infinity. If you put here 1, this will be 0, and if you put 0, this will be 0 again. So this row term will be 0. We are left with only this term, so minus, right? Minus n to the s and n minus 1, n minus 2 upon s plus 1, s plus 2 again, right? So s plus 2. We are left with integral from 0 to 1, 1 minus y to the n minus 3, y to the s plus 2. Now if you look at this pattern, what we can find is that when we do the integration by part, one time you will get this one s, right? You mean our original is what? Our original is s minus 1, right? Our original is s minus 1. So when we do first integration by part, you will get s, right? That means this s minus 1 is increasing, right? Now if you do second again, if you do integration by parts again, so it will be s plus 1, right? Here s minus 1, s plus 1, and you will get again here s plus 2, right? S plus 2, right? And then what about this part is, this is y power part is increasing, right? And again, one is 1 minus y part. 1 minus y is at the first term in is n, and n minus 1, n minus 2, n minus 3, right? That means it decreases. So continuing this way, if you continue this way, so continuing this way, and n minus 1 times, right? So take IBP again, take IBP and so on up to n minus 1 times, we will have that I is equal to limit n tends to infinity, n to the s, and n minus 1, n minus 2, and so on up to 3 to 1 upon s plus 1, s plus 2, and so on up to s plus n minus 1, and the last term will be integral from 0 to 1, y to the s plus n minus 1, okay? Meaning this is decreasing, right? 1 minus y power, this is decreasing, so there will be some terms when this term is dismissed, right? That means it vanishes, right? It will be vanished if you do, right? So we are left with only this term only, so y to the s plus n minus 1. Now this is easy, right? Take integration, so limit n tends to infinity, n to the s, and this, if you see this is nothing but n factorial, right? N factorial upon s plus 1, s plus 2, and so on up to s plus n minus 1. Integration of this is y to the s plus n upon s plus n from 0 to 1. So limit n tends to infinity. If you put here 1, so this will be 1, okay? This will be 1 over s plus 1. So if you put 0, this will be 0. So limit n tends to infinity, n to the s into n factorial upon s plus 1, s plus 2, and so on up to s plus n minus 1, s plus 1. Right, so our integral, our original integral then is this one. This integral is nothing but this limit. So our limit integral from 0 to infinity, x to the s minus 1 e to the negative x dx is nothing but our limit n tends to infinity, n to the s, n factorial by s plus 1, s plus 2, and so on up to s plus 1, right? So what do we have? So this term is nothing but from Gauss expression of gamma function. So gamma s is limit n tends to infinity, n factor upon n to the s, n factor into n to the s upon s, s plus 1, and so on to s plus 1. So this limit is nothing but gamma function, right? So gamma s, so meaning this or whole integral, this will be gamma s, or gamma s is integral from 0 to 1 x to the s minus 1 e to the negative x dx for all real part of s is greater than 0. So this is the proof of integral representation of this gamma function. So this is how I managed to prove this.